Hey, Mom, I spent 8 years on this degree, but I hate it and I really want to change jobs. I'm sorry, I know this sounds crazy. I ended up going with practicum. Practicum allowed me to keep my job and continue working very well. It's a fast-paced industry. It really doesn't matter your current career, what you did in the past.
Hello. 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 Hello.
Hello.
Arguments is what Julia calls method. Functions have methods, plus classes. Which initially, if you were like me coming from object-oriented world, I thought that was going to be a gigantic range of paths. That means for each construct, you need the same set of functions to be defined. Right? It seems obnoxious because I can just inherit. Right. But that's actually true. In C++, it's still there. Actually, you usually do overload parent functions anyway because you want the subtypes. specific things that the parents can't do or should.
Yeah.
So it's just a little bit more obvious how much as opposed to in C++, where it's very much obscured.
Okay.
What, can you hear us?
Recording in progress.
Do you think I make this like bigger?
But it's also what people are seeing on that. I wanted them to see Josh.
Oh, they see this?
Yes, this is what is on Zoom right now.
Oh, I see.
The only real difference is that functions are owned in C++
You don't
by
need,
data.
microphone
classes,
and we're like,
Just furthermore, they're private. Nobody else.
Thank you.
They don't.
All right, I guess we can get started. We're very excited to have Josh to give us this special seminar. The topic is on proving ultralight dark matter and very low density from Earth and space. And let me just say, Josh got his PhD from Cincinnati and did his first postdoc in Weizmann, and now he's doing his second postdoc at IPMU. All right, take it away.
Great. Thanks for the introduction and thanks for the invitation. I'm happy to be here. I realized very first thing, I wrote the date wrong. But anyway, so I'm here to tell you about some work starting a few years ago and continuing today to do with ultralight dark matter and how it can be probed, both in terrestrial and space missions. And I will emphasize throughout the idea of this very local density to be distinguished from the usual local density of dark matter. And so various references are here, two of which I'm hoping will be out in the next month or two. So I won't spend a lot of time motivating what dark matter is. There's a lot of evidence that it exists. We'd like to know what it could be. And in the theory space of dark matter, you've probably seen images like this in many places. The first parameterization of dark matter models might be in the mass of whatever is the fundamental constituent. So there are lots of interesting theories in the very heavy range where you have kind of macroscopic dark matter objects, we probe by lensing and so on. There's been a lot of work historically. Most of the research effort is dominated by this intermediate range where the mass of the dark matter is connected somehow to the weak scale. So, you know, the mass is sort of TeV, but now people are interested in much lighter masses and then also potentially modeling much heavier masses. All of this is very cool and interesting, but it's not what I'm interested in today. I'm interested in the range where dark matter masses are between about an eV and about 10 to the minus 22 eV. And I will just call this whole range ultralight dark matter. You will see in the literature different conventions here. Some people just call ultralight dark matter this very lowest range, but for clarity, I'm just going to refer to this whole range. What's a few things that are particularly interesting about this range. Number one, the dark matter particles in this range must be bosons. You can derive this from a very simple argument. You just look at the energy density that dark matter has to account for, and you ask how many particles will there be occupying a given volume of phase space? What is the typical occupation number? And if the particle mass is below an eV, this is much, much larger than 1. So it can't be a fermion. It has to be a boson. Secondly, this dark matter candidate is wave-like on very large distance scales. So if you just look at the de Broglie wavelength of these candidates for different choices of the mass, you see that you can have quasi-particles, sort of wave-like structures on scales of order Earth size or solar system size or even galaxy size. And in fact, this sets a very strict lower bound on the mass of dark matter candidate if it's 100% of dark matter, because if the mass was any lower than this, then the dark matter wouldn't fit into the size of galaxies we've observed, right? If the dark matter particles are bigger than the galaxy, it's not a good model for dark matter. And so here in this image, I just want to briefly show you, this is a snippet of a simulation by the Xu et al. Collaboration from 2014. You can find it on YouTube. And this is a simulation of a whole galaxy. What you can see, hopefully relatively clearly, maybe it should be bigger. What you see in this image is the wave-like structure of ultralight dark matter in this very lowest mass range. Play one more time. The green and yellow splotches, these are these traveling waves of typical size of de Broglie wavelength. Those are sometimes called quasi-particles or granules. And those travel through the galaxy, they merge and coalesce. They're essentially just traveling waves of dark matter. And in the center of the galaxy is something known as a boson star, which I'll talk about a little bit as we go on. Boson star is the ground state of the ultralight dark matter field. And these simulations suggest that in the center of galaxies, you find large occupation of the ground state. So that's my very brief summary of ultralight dark matter. Let me equally briefly outline what searches for ultralight dark matter sort of look like. And one way I like to think about it is that there are two general kinds of searches. So analogously a little bit to WIMP detection, you have a kind of indirect detection strategy and a direct detection strategy. The indirect detection strategy is something like looking for scalar or pseudoscalar particles being produced by some source, and you look for long-range forces corresponding to this long-range forces or particle production that corresponds to something detectable. So in the pseudoscalar case, this, what I mean by this is things like astrophysical searches, so production of axions in stars or in other astrophysical objects, looking for things like neutron star cooling. These kinds of indirect constraints generally are flat in mass because you're producing very light particles whose energy scale is dictated by the source rather than some intrinsic dynamics. For scalar couplings, this actually appears as a fifth force, a non-1/r potential between two massive objects that are sending scalar particles one to the other. And there the constraints are sort of here. These are both on photon couplings, by the way. But again, over a wide range of particle masses, these kind of constraints are usually flat. And then there's a second strategy, which in this analogy is something like fingers reaching down from the top. So these are direct searches. They're generally sensitive to a more narrow range of masses, but they can reach much deeper down into the parameter space. So for pseudoscalar couplings, this includes things like ADMX and other haloscope searches for axions. And these fingers that are reaching down from the top, they're trying to reach down to this target, which is something like a QCD axion, different flavors. And there are other searches in this lower mass range that I'm going to talk about. In the scalar case, there are also direct searches. This is from things like atomic physics probes looking for variation of fundamental constants. And I'll talk about that a little bit later on, but you can think of these things as the direct searches. And you see that for scalar couplings, the direct searches don't even reach below the indirect searches because the indirect searches are so strong. And the target that everyone would like to reach in scalar models is the first target you might try to reach is just a natural theory where corrections to the particle mass are not larger than the bare mass. This is so naive technical mindfulness. Yeah, we haven't reached there yet over nearly any part of the parameter space. So one way to think about the program that I will describe to you is there a way to enhance the direct searches relative to the indirect searches? So in the right panel here, is there a scenario where these direct searches will be stronger than the indirect ones? And it turns out there is. And it's not super crazy, but what you have to do in order to get there is just question one of the basic assumptions of all of these direct searches, which is what is the dark matter density that we would be sensitive to at the position of our experiments on Earth? What is usually assumed is on the basis of papers like this and similar ones that what does our dark matter halo look like? It's roughly spherical with some overdensity somewhere, but basically in the vicinity of the solar system, the density function is smooth. You can predict it by looking at for example, the motions of stars at a similar position in the galaxy. So this will tell you something like the average density in the vicinity of all the stars that are at the same radius. And from this, we conclude that our sun is probably not special. And so the local dark matter density should be roughly what you can derive from these large scale observations. And you get something like 0.3 GeV per centimeter cubed. This and other observations like this are the basis for how we think about our direct detection searches. So this is what I will call the local density in the usual parlance. But I'd like to distinguish it from what I will call the very local density, which is essentially the possibility that in addition to this large scale dark matter halo, there are overdensities at the scale of the solar system. So none of the kind of observations that I've described to you would be affected by this because the average dark matter density across the whole galactic midplane would be the same, right? And as I will describe, there are lots of both known and well understood density fluctuations and also weak constraints on this model. And there are hints of dynamical processes that would cause such overdensities to form. This is ongoing work, but I would give you kind of a flavor of what we're working on. In the presence of one of these very local overdensities, we can predict unique signals in terrestrial experiments and also in space missions. So if you put experiments at other positions in the solar system, you can have very novel predictions there as well.
Sorry, but you assume that the additional mass, right, from this overdensity is small compared to the mass of the object itself, like star system also. So you don't get any effect from, enhanced lensing or something like that.
Exactly. That's right. This is sort of a common sense constraint on this situation. If there's more dark matter in the solar system than the mass of the sun, then you've violated dozens of constraints.
I mean, if you look at some star, right, and you know pretty well its mass and its planets, and I think you can predict maybe with a good accuracy, right, the mass of the system, right, even if it's a distant star system, right?
Mm-hmm.
Yeah, and then from lensing you can compare. So what I want to say is that maybe it's not like 100% of the solar mass. The constraint, maybe it's stronger than that.
For sure. So what we believe to be the strongest constraint on this, at least in our own solar system, is from what fraction of the sun's mass could really be dark matter before you disrupt solar processes, right? And there's not very many groups have actually looked at this because the kinds of people that are studying solar processes usually are not looking at dark matter. But the constraint seems to be at most at the level of maybe 5 or 10%.
Well, that's still not 100, right?
Yeah, for sure. So yeah, we make sure that we satisfy these constraints conservatively. Okay, so let's start by introducing some of the kinds of bound states that will be relevant here. And to do this, we'll return to the equation of motion for the axion field. So briefly, you can start with a relativistic theory with a field phi, but ultralight dark matter, as all other dark matter, it's cold and non-relativistic at late times. So you can expand this relativistic field in terms of a non-relativistic wave function. And because I'm interested in real scalars for the moment, there's a sort of complex conjugate here, and a factor of 2 that matters. But in any case, the equation of motion is basically the same. So if you start from the Klein-Gordon plus Einstein equations, you can reduce them in the non-relativistic limit to a nonlinear Schrodinger equation, sometimes called a Gross-Pitievsky equation, coupled to a Poisson term for gravity. So in order to solve this system, you simultaneously solve this Schrodinger equation with a Poisson dictating the gravity of the field. And I've included a term here for an external source, which is not made of axion. So this will represent the sun or the earth or something like this a little bit later. And by way of review, let me just remind you or tell you, if you haven't heard before, the ground state configurations of this system, when there's no external potential, when you're just looking at the self-gravity of the star, the ground state is what's called a boson star. This coupled system of equations is actually very straightforward to solve. Here are some of the profiles for these boson stars. There are a few interesting facts about this. For example, that as the central density grows, the mass of the star grows, but the radius shrinks. So there's this inverse relationship between the radius and the mass of the boson star. And up to a factor of roughly 2, this is the precise radius of the star, defined to be something like the radius within which 90% of the mass is contained or something like this. This is dropped exponentially. You can also get the same scaling, by the way, by just looking at how these two relevant forces scale in equilibrium. So the kinetic term just goes like 1 over r squared with a plus sign because it's repulsive. The self-gravity term goes like m over r with a minus sign because it's attractive. And when these two things are balanced, you just solve for r as a function of m, and you arrive at this expression as well. So this configuration is sometimes called a dilute boson star because it is dilute. You can see that the size can be very large, especially when the particle mass becomes very small. So that is a boson star. These have been studied for, by the way, 50 or 60 years. The first solutions for boson stars were Kaup in 1968. And yeah, there's been kind of a renaissance of boson star studies in recent times, including things like simulating formation of boson stars. So it's been asked for many decades, great, you have a ground state of the system, but do you actually, in a realistic system, is the field actually driven to the ground state in any significant way? The answer seems to be yes. One of the simple ways to understand this is just to look at gravitational relaxation of these quasi-particles, these traveling waves that I showed you in the halo in one of the first slides. And you can do just a basic, astrophysics 101 kind of calculation for the gravitational relaxation rate for these quasi-particle objects, exchanging little bits of energy through gravitational scattering. And the usual story here, people talk about this in the context of stellar collapse in galaxies. The story here is basically that these objects, these quasi-particles, can be very heavy for ultralight dark matter. And they will exchange small amounts of energy through gravitational scattering. Some of them will gain a little bit of energy, some of them will lose a little bit of energy, but this happens many, many times over the lifetime of a halo. And after a typical relaxation time, which is proportional to the crossing time for a given scatter, these waves, a significant fraction of them will change their velocities by order 1, which means some of them can go to their ground state and some of them can be kicked out of the halo and so on. And that's
but isn't it just Jeans instability what you're saying? Just Jeans instability, because there is just gravity force involved, right? Nothing else.
It's not quite the same because you can start, for example, with a totally stable, in the usual sense, virial dark matter halo, and then you wait some time for gravitational scattering. And
well, but you see there are some homogeneities, right? Even that you should add.
You mean in this simulation?
Yeah.
So
Maybe you are in the halo, but there are homogeneities which you have to add if you want to form. At least that's what flows from these two pictures.
It might be that I'm misunderstanding your question, but for example, in this simulation, what they tried to do, so this was not sort of realistic halo parameters, but they wanted to start with as generic an initial condition as they could muster. So they took basically white noise for the distribution of momenta. So yes, there will be fluctuations, but there was no initial seed of an overdensity per se. And what they still find is that through gravity only, some fraction of the waves in this box relax, and they always see formation of boson star at some random point in the box. You actually couldn't predict the formation point of the boson star because the initial condition is so generic.
But there are still overdensities, right? I can see overdensities.
Yeah, I mean, of course, like it's not truly constant over density, not a truly constant density system. Because in a truly constant density system, you wouldn't have these traveling waves at all. And, it's not really particular. What's interesting, especially to me, is that you can do this like astronomy 101 calculation, and you compare it to the time scale found in these simulations, and it's spot on. Yeah.
And how do you define boson star, the axion star, when it forms? Do you define it just by the density or just by the profile of the?
So they can fit the density profile of this thing to the analytic profiles of this one that I showed you.
And is there some criterion that you have to satisfy to call it a boson star? Or?
I'm sure there's a precise criterion, but commonsensically, you can see by eye how well this density stands out from the background density.
I mean, it should be approximately the same. Some equations more, it should be long read.
Yeah.
I don't remember what criterion they use in this. And I want to point out, the simulation that I showed you on the previous slide is certainly not unique. So I told you that it used a kind of generic white noise initial condition, but you see formation of boson stars in numerous other simulations, including the Shiro collaboration simulation that I showed you in a previous slide. There's an independent simulation by Mox et al. With very different initial conditions for the dark matter field. And they also see formation of one massive central soliton in each galaxy. And even for very different parameters, I was talking to Raymond about this a little bit earlier. This is a simulation for QCD axions, where boson stars are observed to form inside of smaller scale over densities called axion mini clusters. So in this simulation, they took realistic profiles of axion mini clusters from cosmological simulations, and they further evolved them, and they found very rapid formation of boson stars in those over densities. So at least in a wide variety of scenarios, boson stars appear to form, and they appear to form quickly enough that they're astrophysically relevant. But the configuration that I mostly want to tell you about today is slightly different. But I went through all of that background to kind of draw some analogies between this more novel configuration compared to the one that's been studied for 60 years. So this is a configuration that we call by various names, but you might call it a bound bosonic halo. Bound because it is bound to some external gravitational source, which I will just write its mass as m external. So in the same way that we solve the equation of motion for the boson star, we can do the same thing, neglecting the self-gravity, but now including the external gravitational source. If you again balance these two forces, you find a very similar expression for the radius, but you see that the radius no longer depends on the mass of the bound dark matter. The radius only depends on the mass of the external object. This is, of course, in the limit where the mass of the boson star is much smaller than the external mass, which is the common sense constraint that we discussed earlier. But other than that, this M star is a free parameter in this theory. You have the same configuration. You can put more and more mass inside of it, and it doesn't change in size. It only increases in mass and density. So the dashed lines here correspond to configurations of the same central density as the boson star, but these are exponential profiles because they solve this hydrogen-like equation of motion. So the picture that I'm advocating here is something like the following. So in addition to the usual dark matter background that is dictated by galaxy scale dynamics and virialization of the dark matter field and so on, there can be bound states around astrophysical objects whose size is essentially determined by the host object and the particle mass. And what's neat about this is that it's very predictive in terms of what is the interesting mass range for each object. So for example, if you want to detect this solar halo from the position of the Earth, you need the size of the solar halo to be at least an AU. This fixes a specific range of masses larger than about 10 to the minus 14 eV. And if you make this thing too big, if you decrease the radius then this size quickly grows very, very large. And if this is the size of, say, parsecs, the distance to like the nearest star, then you would be saying that there's an overdensity in the whole dark matter halo, right? Which would again violate the observational constraints. So there's really only a few orders of magnitude of interesting mass parameter here. So it's fairly predictive in that sense. And similarly, if you wanted to look for a bound halo around the Earth, the typical, if you want the typical radius to be about the Earth radius, the mass you're interested in is about a nano eV, and you can go a few orders of magnitude larger than that before you start to run into other planets or the sun or something. So in this talk, I'll focus on the solar case because that's where most of the work has been done. But if you're interested and there's time, I'll talk about what happens to the Earth. So you are asking in your minds, does this actually form? And I can confidently say, it's a topic of ongoing work that I was hoping to have done by now, but it will be finished in a short amount of time. But let me give you some flavor of the kinds of things we're thinking about in lieu of actually showing you our results, which I'm not ready to show. So firstly, I gave this analytic explanation for how ordinary boson stars form. And what sort of led us down this road in the first place was the observation that, suppose you have a very similar system of quasi-particles scattering around, but now you put a very massive central gravitational potential somewhere in the system. When these quasi-particles scatter against each other, some of them will lose energy and go towards the ground state. Some of them will gain energy and get kicked out of the halo or to larger radii. But the ground state of this system is a bound halo around the sun. There's a very deep potential well. And if the quasi-particles are actually sampling different energies and they have the ability to go to the ground state, that is the ground state. So just in a hand-wavy analytical way, the same dynamics should apply to this system as it did for the boson star. Of course, that's not a proof that this actually happens, that it's parametrically fast or anything like that. But if you waited an infinite amount of time, it seems clear that you would find a lot of bosons found around the sun. Secondly, although ultralight dark matter has not been studied for as many years as cold dark matter, there are ultralight dark matter simulations, some of which I told you about. And although most of them don't include baryons, there's one that I am aware of that includes at least a preliminary idea of what baryons are doing, just through their gravitational interaction. So what this simulation does, this is work by Veltma, Schwabe, and Niemeyer. So they looked at the evolution of an ultralight dark matter halo in the presence of a central baryonic sphere in the center of the simulation that did not evolve. So they were not looking at interplay between baryons and ultralight dark matter. They just wanted to know, if you put some baryons in there, how will the evolution of the ultralight dark matter field change? And the answer is very similar to the story that I told you on the previous slide. So if you compare their dark matter densities as a function of radius, here the blue lines are fuzzy dark matter, ultralight dark matter with baryons. The orange lines are just CDM, so no wave dynamics. And green is FDM only. And these are two different snapshots in Redshift. And what they find is that at early times, the FDM with baryons and the FDM without baryons were sort of similar as the soliton starts to form, but they very quickly find a big difference. So they find, comparing the green line, which is ULDM only, they find this smooth soliton with like few orders of magnitude larger density than the background. If you included a baryonic potential to the same simulation, you found a few orders of magnitude, or one to two orders of magnitude larger density and a very different shape. So if you compare the shape of this profile to the shape of this profile, you actually find that the shape of the blue curve is much more well approximated by the exponential function that I described as being relevant for the bound bosonic halo, as opposed to the green shape, this very wide chord shape that is relevant for a boson star. So just to say it again, The green curve is the usual formation of the soliton in the center of the ULDM halo. The blue curve appears to be a large amount of ultralight dark matter getting bound around this central gravitational potential. They furthermore found that the presence of this baryonic core actually accelerated the appearance of this bosonic core. It did not slow it down. You more quickly formed a large density core when you included baryons.
So sorry, but the tail is a power light or exponential light? So if you look at it really large distance, it's power light, right?
Well, this is like NFW, right? So in all of these cases, for very large distances in the ULDM halo, you map onto something like an NFW. Because at large distances, there's no effective wave dynamics. So that's why all of these, including CDM, they all basically create a large distance.
So you have some, additional central silicon, and you can see that there is a special follow at not so large distance, right? You can conclude that there is an additional silicon on top of this structure, on top of this green line.
On top of the green line, you mean comparing the blue to the
Yeah. So like blue line, it looks like the difference between the green line and the blue line is that you have a soliton on top of whatever you have. Whatever represents a green line, you have an additional soliton.
So yeah, so the way that the authors interpret this, and also how I would say to interpret this, is that the green line is the soliton mapping to NFW at large area, right? That is the usual soliton, which is only slightly more dense than that you would expect from this first point of the NFW. If you include the baryons, then you still map to NFW at large distances, which it must, but you get larger density, you get density faster, and the profile here is less chord. You can sort of see it by eye. They explain even different. So this is a very different system than the one that I will describe to you, because this is galaxy scale, and what I will describe to you is solar scale, and there are more complications to do with the difference in scales, and also the fact that the sun is moving through the galactic background, whereas this is all kind of at rest. But the same dynamics hold, and so this is the kind of thing that we're analyzing in our work. So I just want, yeah.
Oh, sorry, I'm missing something basic. So what exactly is the interaction that they're adding between the baryonic core and dark matter?
Just gravity.
So why does that? So what makes baryonic core special compared to this host mass? So what is baryonic called?
That's right.
They call it baryons because they thought of this as a first step towards a realistic simulation of ULDM plus baryons. Okay. But there's nothing that actually makes it baryons. This could be another flavor of dark matter. Okay. Could be a black hole, whatever. Didn't really know. Okay. They just fixed the size and mass of the central thing, and they evolved the ULDM field to see what it was.
I see.
Okay. Here's a third, very different kind of hint that might suggest it's not crazy to think about a lot of ultralight dark matter falling onto stars. And this comes in the form of something like action. So here's the story. The story, which was first pointed out, I think, in 2007. I mean, adiabatic contraction is very well known. But in the context of dark matter around star-forming cores, I think the first paper was this one in 2000. So imagine that at early times, before the sun ever formed, you have a molecular cloud, and this molecular cloud has many star-forming cores that will eventually collapse to form stars, and one of those will be our sun. If you have a small, very, very small fraction of dark matter that becomes bound to these clouds, and in particular bound to these cores as they're collapsing, then the collapsing baryons will gravitationally pull the dark matter with it. So if you start with a very low density dilute configuration, the drag of the baryons will pull the dark matter into a more dense, centrally located configuration. This is known as adiabatic contraction, and it's well known and well understood. So you can imagine, just again, a cartoon picture, you start with a star-forming core in the presence of a dark matter background. It gets dragged down until it reaches this kind of small configuration centered around the sun. And in this paper, they point out, using some like pretty basic parametric arguments that even a 1 part in 10 to the 10 initial abundance of dark matter bound to this core, after adiabatic contraction, will give rise to a bound state that is of the same order as the local density. So this is a very, very, very small amount of dark matter that you need initially bound to give rise to what we think of as a pretty large density bound around the sun.
So here you assume that the time scale at which it becomes bounded is not large, at least not larger than the time scale of formation of this of star formation, right?
Well, I might have said it the opposite way, right? That you need the dark matter to be bound on time scales that are at least long enough for this core to collapse.
Right. No, I mean the bound time. I mean the time at which it becomes bound, right? Not the bound time. But,
like this time, going from the left to the right, what I would call the collapse time. Is that what you mean?
Yeah.
Yeah. That's
so
right.
this has to be smaller than the response, you know, the response,
Yeah.
the response time is smaller. Than
Yeah,
the response
that's
time. That's why it's adiabatic, right?
That's right. Yeah. This is assuming an adiabatic limit, which may or may not be appropriate. So that's not answered in their paper, but this kind of got us thinking about a slightly different avenue. So I label all of these things hints because I don't have concrete results for you, but they are coming. And in the meantime, what I want to tell you about is why you should care, which is to say why this is interesting phenomenologically. It's interesting for experiment. And so that's what I'll talk about in the next section. So please be on the lookout for our paper coming soon. But in the meantime, I will just assume that such bound states can form. I will take its density to be a free parameter and look at the constraints on that from direct observation and see how signals in experiment can change. So first thing you should ask is, what are the constraints on this model? So I can't put an infinite amount of dark matter bounded on the sun or the earth. But what's the first thing that I violate if I try to do this? The first thing that you violate actually is, well, it's different for the earth and the sun. Let's focus on the sun. For the sun, what you mess up first is the perihelion precession of planets. So humans have been measuring the orbits of planets around the sun for hundreds or thousands of years. We've gotten really good at it. And if you put a lot of extra matter around the sun, this will change the rate of precession of the orbits of the planets. The precise way to think about this, maybe precise is the wrong word. One helpful way to think about this is that you can compare the orbits of two different planets, because if you look at any one planet, up to a certain amount of additional mass, you could assume that a 1 part in 10 to the 5 fraction of the sun's mass wasn't really the sun, but it was really dark matter. And then the prediction of the perihelion precession of the inner orbit would not be changed. But you can very strictly constrain the mass between two orbits because there's no additional sun to kind of roll that mass into. So the precise thing you can do is comparing two orbits, and in the inner orbit, make sure that you don't violate the constraint that the sun has to be the sun. And this is what the constraints look like for 6 relevant planets in our solar system. This is based on the work of Pijev and Pijeva, 2013, who have this complicated model and took into account large asteroids and all this kind of stuff. It's very cool work. And what I've plotted alongside each of these is the density profile of a maximal solar halo for a given particle mass. So these are really exponential profiles, but we're living mostly in the cores of these exponents. So when the particle mass is small, let's say below 10 to the minus 15, then the size of this thing is as large as the size of Saturn. And in that case, you are constrained by whatever the strongest constraint is in our solar system. But as the mass becomes larger, the size becomes smaller. So you become less and less constrained by the outer planets. And you see that at very low masses, the constraint is very weak. So in principle, you could have a very large overdensity within the radius of Mercury without violating any constraint, but you can't see it on Earth because the density on Earth would be much, much less than that local dark matter density. So again, the interplay between these two things, you can't have this thing too large or else it's much larger than our solar system. You can't have it too small if you want to actually see something. This sets the range of masses that is interesting for us. I do want to point out, this is preliminary work that will come out in the next week or two, I think, that asteroids are actually a good probe here. So there are some particularly well-measured asteroids because governments think it's really important to keep track of asteroids that might hit the Earth, for example. So they measure these orbits super well. And it turns out that some of these asteroids could be competitive with planetary constraints. And one of the interesting, so these red dots are preliminary, like solid constraints. These blue ones are more tentative because they're based on a much simpler analysis. But what's cool about the blue asteroids is that they are on highly eccentric orbits. So some of them, the length of the blue lines correspond to the minimum and maximum distances to the sun. So in principle, asteroids that are on very near sun orbits are probing dark matter densities at very low, small distances. And so even if the constraints themselves are not so competitive, the fact that they're probing to very small radii actually is probing these bound states. So this is preliminary work. The paper will be out soon, but I would show you. So at the end of the day, you use what is at present the best constraint, which is these planetary constraints for the solar halo. For the Earth halo, the analogous constraints come from comparing lunar laser ranging to the orbit of the moon. And so you can constrain how much dark matter could be in our atmosphere. And as you might expect, the constraints there are much, much weaker. You can be sort of 10 to the 18 or 19 above the dark matter density before you start to violate anything. But for the solar halo, it's a bit more modest. So actually the constraints are at the level of 10 to the 4 or 10 to the 5 of the local dark matter, which is still interesting.
Sorry, can you say again how to constrain the Earth's halo? They assume that it is as large as Moon's orbit.
So the analogous thing that you do here, so you want to compare two orbits. Because if you compare one orbit, you could absorb part of that mass into the mass of the Earth. Right? So you compare the orbits of, for example, the Lagos satellite, which is a low Earth orbit satellite, to the orbit of the Moon, which are both measured very well. You can constrain the amount of dark matter between those two places.
Oh, that's interesting.
So these are the current constraints. And if you translate this into how much additional mass in dark matter you are adding, this is what you find. So the maximum amount of mass is given by these black lines for the solar halo and for the Earth halo. And you see that actually in the region where you have the highest density enhancement, you actually have a very, very small amount of additional mass. This is like 10 to the minus 8 to like 10 to the minus 12 of a solar mass. Very, very tiny amount of additional mass we're asking for here. Another way to look at this, I like to explain it this way. So this is, again, the same figure, just focused on the solar halo. This is the size of the solar halo corresponding to a given mass. And these contours correspond to different astrophysical amounts of mass that we're suggesting could be there. So if you add one Jupiter mass to the system, then you get constraints at this level. If you add merely a small asteroid mass, you can still get density enhancements of almost 10 to the 5, and so on. So you should imagine in this case, like one asteroid of dark matter spread out over an AU or 10 AU or 100 AU. This is actually a very, very small amount of mass that would need to be bound in order to have the kinds of effects that I'm talking about here. Furthermore, the other thing that makes this interesting, so you might think I'm just going to show you a bunch of rescaled sensitivity curves, or anything just scaled to the density. And that's part of what I'm doing. But there are other interesting differences in the shape of the signal and in the properties of the signal. For example, when you have virial dark matter, which is what everyone's looking for, virial dark matter has a particular coherence time dictated by the virial velocity in the halo. So it's like 10 to the minus 3 in units of C. The coherence time is like 1 over mv squared. So it's like 10 to the 6, 1 over m oscillations of the field. That's the figure of merit for these axion experiments. But if you have bound states, then the effective coherence time is much longer because the axions in the bound state are much colder. So they oscillate for many more cycles before they decohere. And so in a range like, take for example, 10⁻14 eV, where you might have thought the coherence time was only a day. And so maybe you built your experiment to take data at a certain frequency for 1 day. Actually, if a solar halo is relevant here, the appropriate decoherence time scale is more like a year as opposed to a day. So you could be collecting signal and adding coherently to your signal for much, much longer than you might have assumed. And similarly for the Earth, of course. In the right figure, I'm just showing what would be the effective enhancement to signal if you integrated for the full coherence time in the bound state, because the signals in these experiments generally grow as square root of time. So this motivates slightly different search strategies in these sim experiments. So what are the kinds of signals that we tried to look for? I'll go through this fairly quickly because this is a little bit in the weeds, but we initially in our first, not these papers, in our first 2 papers in 2019, we looked at what were the kinds of experiments that could search for this. And the first one we looked at were atomic physics experiments where the direct detection fingers were weaker than the indirect detection ones. So this is a scenario where the direct detection can be stronger than indirect detection. What do these atomic physics experiments look for? They look for variation of fundamental constants that are sourced by scalar couplings of the field to, for example, F mu, or to the electron mass is another typical target, or to the gluon field strength, and so on. So in these atomic physics experiments, actually fairly similarly to what I told you about comparing 2 orbits, they need 2 atomic systems with different sensitivity to this coupling that they can compare, because if you just measure one energy and the measurement you're making also depends on this fluctuation, then you will always measure the same thing. You'll never be sensitive to the fluctuation. So you have to compare either two transitions, or you have 2 different atomic clocks. Then you can figure out what is the oscillation here. So this is pointed out by several people over a span of a few years. But importantly, this is sensitive to the density of dark matter at the position of the experiment, so-called very local density. So this is just an example. If the ruler you use to make the measurement is changing, then you need to use 2 different rulers, which is to say 2 different physical systems with different sensitivity, and then you can see the relative change. Results. So supposing you had atomic clock searches for this scalar photon coupling at the level of 10⁻14 sensitivity to fluctuation of fundamental constants, or 10⁻18, which is, according to my colleagues, this is doable in the near future with optical clocks over a wide range of masses. You can indeed probe below this flat 5th force kind of sensitivity curve. Furthermore, there are proposals of a nuclear clock, which would be sensitive not only to this alpha coefficient, but also to couplings to the gluon field strength. And there are huge technical advantages to nuclear clocks, which are only now being proposed and being built. But if you believe the projections that the clock people are making, this would be a many orders of magnitude enhancement and potentially get us to almost reach the naturalness line, which is really the goal of all of these searches. This is for searches on the Earth, and I promised you searches in space as well. In the few minutes I have remaining.
Sorry, what is HP? No,
okay. So this is just another benchmark. This is a Higgs portal relaxion. So relaxions generally have Higgs-like couplings with some mixing angle, and if you require that it's a good relaxion, so it solves the hierarchy problem for you, then you maximize the mixing angle consistent with that, and so you get this other constraint. In the few minutes I have remaining, I want to tell you about space searches. which is a recent paper with Yudad Tsai and Mariana Safranova. So as I pointed out before, these constraints are all radius dependent. And if you have relatively large particle masses, like above 10 to the minus 14 eV, almost to 10 to the minus 13 eV, the size of these solar halos can become very small, such that you wouldn't see anything on Earth, because at an AU, the density is very low. But if you had a probe at much smaller radii, you would be sensitive to these objects. So it is, again, highly consistent with every current observation that there is a huge dark matter overdensity of some size, doesn't have to be maximal, but there's a wide range of possible densities of a small core of dark matter around our sun. And how would you ever know? Well, you have to go there, right? You need a space search. So we should be wary of hubris, because you may recall the famous myth of Icarus, who had these waxen wings and he flew too close to the sun and they melted and he fell. But what we can do that he did not was that we can bring a heat shield, and that will help us not melt as we go to the sun. So this is an image of a space mission. I'll tell you about it in 2 slides.
There is, for example, part of solar.
That's exactly the one. Yeah. So first I want to tell you that there are many proposals to bring clocks like the ones we use for our sensitivity curve, many proposals to bring atomic clocks to space. There's a mission in space currently from NASA and also from China, who have demonstrated stability at the level of 10 to the minus 14 for atomic clocks in space. There's a proposal from France also that has a target towards a magnitude better, and this will rapidly advance. The reason it will rapidly advance is, again, because governments want to do this. They have lots of non-science, non-fundamental science reasons to do this anyway, including better timekeeping on the International Space Station, improved GPS on Earth, also spacecraft navigation. If we achieve this dream of going to Mars, we will need high precision clocks in space to communicate between the 2 colonies. These are the kinds of things forward-thinking people are thinking about. And we just want to say, with minor modifications of these proposals, you could do ultralight dark matter detection, because you need the same kinds of clocks in order to do this. And yeah, as you correctly intuited, another motivation for this is that humanity is also interested in going close to the sun. There is this ongoing mission called the Parker Solar Probe, which has reached distances down to 0.06 AU, which is the closest any non-self-destructing human-made object has ever come, and it will go even closer. They have a lot of complex electronics and machinery on board. They have magnetic shields and heat shields to protect the instrumentation from the various harsh conditions near the sun. They're not exactly what we need for atomic clock missions, but in discussions with some of these Parker Solar Probe scientists, they're actually not that different. The kinds of things they've already sent here and what we would actually need to protect an atomic clock. So suppose we did a mission like this. Suppose we sent a Parker Solar Probe-like object carrying an atomic clock with 2 states or 2 atomic clocks to make this measurement. Here's what the sensitivity would look like. So the black curves correspond to the 3 benchmarks that I told you already for terrestrial searches. If you had a probe that reached the orbit of Mercury, so now you're sensitive to smaller masses because the solar halo mass can be somewhat larger, so its radius is smaller. The red curve starts to reach basically to the naturalness line exactly. And if you could go inside the orbit of Mercury down to 0.1 AU, which is still a factor of 2 larger than what's already reached by the Parker Solar Probe, you potentially have this huge boost in sensitivity coming from the fact that we don't know what the density is here. So so there are kind of 2 avenues of attack here. One is, what is the direct constraint, and secondly, what I described before, what is the plausible or possible density enhancement that could actually form.
But what's the characteristic time scale of the mission? Like how long do you have to be near the sun to make this?
Not very long, especially at high masses. So the time scale here is faster, right? The frequency is higher, so the time scale for oscillation is faster. So if you have a clock that is optimized to these high frequencies, you need relatively less time to make the measurement. I don't know exactly what the number is.
Minutes, months, years?
So, I mean, your sensitivity is going to grow as square root of t, up to some maximum coherence time, which up here could be months.
Okay, so these are kind of ideal curves, assuming there is no constraint from time observation time.
Yeah, that's basically it. So yeah, as I've already pointed out, there's a lot to do, both on the space probe side. We have discussed with NASA scientists about what is the kind of temperature or magnetic field fluctuation the Parker Solar Probe already experiences. And comparing this to our clock colleagues, actually pretty minor modifications of the existing heat shield technology would be relevant. Actually, we were very worried that the temperatures would be so high, you would just melt any atomic clock, but they can keep the temperature variation below 40 C, which is totally fine. It's actually cold temperatures near the sun may be more damaging to us than hot temperatures, which is neat. On the clock side, there's a lot to do too, because you also need lightweight clocks optimized for this high frequency run, possibly different clock infrastructures so that you could measure different couplings and so on. But anyway, people we've talked to seem very intrigued by this, and so we're excited about it. Last thing I'll say maybe is just that there are other couplings you could search for. I mentioned this briefly already. If you have microwave clocks, for example, it's a different quantum clock infrastructure, but microwave clocks are sensitive to variations in the electron mass. And nuclear clocks are really the only clocks that would be sensitive to these nuclear couplings, like coupling to the field strength or quark masses. So that's all promising. There are other implications that I don't have time to talk about, including Earth halos. It turns out going away from the Earth is not helpful if you have an Earth halo, because you're actually getting farther away from the density. Whereas when you go towards the sun, you're going towards the density. So we don't actually want, I mean, we want them, but there's no advantage to going to space if you're looking for an Earth-based halo. And the very last thing is just that there are interesting modulation effects in the signal when you have searches for pseudoscalar couplings, which I didn't really go into. When the signal is proportional to the gradient of phi, both the position and orientation of your detector will affect your signal. So this motivates possibly network searches with different, you could have different low sensitivity experiments around the Earth. The GNOME network is an example of this, actually. We've talked to them about this. If you orient these things differently and you put them at different latitudes, you could map out, what is the velocity structure of this bound halo. And so it could be a unique probe. So I'm going to talk about that. In conclusion, there are lots of interesting ultralight dark matter bound states, including boson stars, and also, we think, bound states in the solar system. I do promise you that we have work coming that will be able to predict or at least bound what is likely for the density of these bound states. But it has big implications for direct detection. And so one thing we're trying to emphasize is, there's a lot of work being done to try to precisely map the density and velocity structure of the dark matter halo. But if you're not taking into account things at small scales, it's not relevant for your experiment, right? So you can understand the Milky Way halo as well as you want, but if there's a density fluctuation at the level of the solar system, all of that work is not that helpful to you experimentally. So it's really important to understand things like this. With that, thank you for your time.
Thank you for the very nice talk. Any questions from the students? Postdocs?
Going back to boson stars.
Yeah.
So you mentioned that people simulate how boson star can form in the center of galaxy, for example, and they take into account gravitational potential created by baryonic matter.
Yes.
But even then, there is an additional thing, right? We know that there are supermassive black holes inside of the galaxy.
Yes.
And this supermassive black hole is something that you cannot neglect its presence, right? Because on the one hand, this axion cloud or soliton, it can affect properties of the black hole. For example, it can, change how it grows, right? Change the growth rate. And on the other hand, the black hole itself can affect the properties of the soliton, right? Because in principle, you can think of it as a black hole with a scalar hair, right?
Mhm.
Something like this type of configuration. So, do people take into account this?
So at the level of these kinds of simulations, no. So my guess is what these people would say, not to speak for the simulators, but what it seems like they had in mind, and they also said this when I talked to them, what they call like the effect of baryons could be the effect of any gravitating matter in the center of the system, right? So all they're doing is including some additional mass with a given mass density. So this could be a black hole, this could be a baryonic.
Yeah, well, black hole is because once it's black hole, it doesn't matter what it is, right? Then it's
Sure. Yeah.
So
it's at some level it is taken into account here in the sense that the mass that they include may as well be a black hole. Like, there's nothing about it that makes it baryon-like.
yeah.
Now, if you're worried about things like the mass radius relation, like it has to satisfy the Schwarzschild relation, I'm sure that that's not what they're doing. But as long as you're like very far from the center of this thing, then that shouldn't matter either. I think the other answer to your question is that there are people, for example, I think Kurt Bloom has a couple of papers about this with his student and maybe Sergei Sibiryakov. I'm not sure exactly which authors are on which papers, but they have looked at what happens if you just assume you have one of these solitons. You don't look at formation or anything. You assume you have one of these solitons in the presence of a black hole. And how do those things interplay? How does the soliton get eaten by the black hole? How does the, this kind of thing. How does the radius of the soliton change in the presence of this central black hole and so on? So there is some work on that. It's not the level of simulation, it's more at the level of, solving some algebraic equations and doing some simple numerics.
But this can give you many potential. They look at black holes. That also black holes. And on the other hand, we have supermassive black holes. They should form somehow in the universe. It's not completely understood how they grow with such a fast rate, right? And maybe this additional dark matter can assist the growth. So there are all sorts of questions.
Yeah, that's very interesting too.
One more quick question. So you mentioned that you only need a minor modification to the atomic clocks to do your measurements. So what are the modifications that are needed?
So it depends a lot on how these kinds of missions are, what actually happens with these kinds of missions. When I say minor modifications, I mean the same kinds of clocks can do all of this stuff as the kinds of clocks we need. The main difference is that we need a clock that is, we either need two clocks with slightly different, different isotopes, or one clock that measures two transitions. Both of those are straightforward to do on Earth, but these missions don't necessarily need that. They only need one to do what they're doing. I think that's the biggest difference. We also think that a nuclear clock would be especially useful for our purposes because it's sensitive to multiple couplings and with very high sensitivity. Whereas I'm not sure, like it might be like a cost and weight issue on the other side, right? Nuclear clocks are very new and cutting edge. It may be very risky to try to put one in space in the near future. So we might be stuck with optical clocks, which are also interesting. There are a few like optimization things that would be important for us that may not be important for the other missions. For example, To probe this high frequency range that is especially relevant for us, you really need to optimize the clock running to a particular frequency of like tens of hertz. Whereas for other missions, you may be optimizing for something else.
But isn't it possible to send a pair of one level clocks instead of somehow achieve levels of communications so at different distances? Right?
Compare two clocks at different distances.
Yeah. So you can send either one clock with two levels, right? Or you can send two clocks, one level clocks, but different. Is it possible? Is it better or worse?
At this level of analysis, it's the same. The sensitivity that's assumed here, I have some backup slides if you want to know more about the technical issues around clocks, but these assumptions are based on what is possible on Earth, but the clock infrastructure doesn't actually matter that much. Like there are some clocks that are optimized to look at two transitions, some that are two different isotopes. There are also linked clocks at different positions of the Earth, and they do analysis this way. So there's many ways that this could be done.
Okay, no more questions. So let's thank the speaker again.
Interesting. Went to sleep.
Stop. So,
Hold on. Yes, later.